This Module 24, the chemistry of life, organic and biological chemistry. By the end of this module, you will be able to distinguish among alkanes, alkenes, alkynes, and aromatic hydrocarbons. Also, you'll be able to draw hydrocarbon structures based on their names and name hydrocarbons based on their structures. And finally, you will predict the products of addition reaction and substitution reaction. We are all familiar with how chemical substances can influence our health and behavior. Aspirin, also known as acetylsalicylic, relieves aches and pain. Cocaine is a plant-derived substance that is used in clinical situations as anesthetic, but is also used illegally to experience extreme euphoria or high. Understanding how these molecules exert their effects and developing new molecules that can target disease and pain is an enormous part of the modern chemical enterprise. This chapter is about the molecules composed mainly of carbon, hydrogen, oxygen, and nitrogen that bridge the chemistry and biology. Also, we have the organic chemistry. Organic chemistry is basically the chemistry that studies the compounds that contain carbon, and biochemistry is the study of chemistry of living systems. Here in our left, we can see a PET scan of a human brain that shows the metabolism of glucose metabolism in a normal brain, and how this glucose metabolism is repressed due to the use of cocaine. And we can see here in the red and yellow is basically that metabolism, and we can see here how that the use of cocaine repress that metabolism in the brain. So let's talk about general characteristics that we have studied before, and that is going to help us a lot to understand these concepts. First of all, is that carbon makes four bonds. They are the main element in family 4, and they can make 4 bonds. All single bonds, tetrahedral, there is known as hybridization of sp3. As we can see here, we have a carbon in the black sphere. We have 4 hydrogens around it, and the shape, the geometric structure is tetrahedral, and the angles between those carbon hydrogen bonds is 109.5, and the hybridization of this carbon is sp3. When we have one double bond, we know that that part of the molecule is trigonal planar, and the hybridization of that carbon is sp2. And in this side, this part of the molecule is a trigonal planar. We have here three types of bond: one double bond and 2 single bonds, and the angle between these bonds are 120 degrees. And we also have the triple bond that we know is a linear one, and that hybridization of this carbon is sp, and the angle between this single bond and the triple bond here is 180 degrees. Remember, that's sp3 tetrahedral, sp2 is trigonal planar, and sp is linear. The carbon hydrogens are the bonds, most common bonds that exist in molecules. Carbons form strong bonds with many elements, including other carbons, hydrogens, oxygen, nitrogens, and halogens. Groups of atoms that determine how an organic molecule reacts are called the functional groups. So that part of the molecule that is reactive is due to the presence of a functional groups, and we're going to see in a few minutes some of this. Actually, not in this model. In the next model, we're going to see some examples of functional groups. Now let's talk about the solubility. Most prevalent bonds are carbon-carbon bonds and carbon hydrogens. These are nonpolar. Carbon-carbon has basically the same electronegative as well as carbon hydrogen, so these bonds are nonpolar. So the solubility in water is really low for many organic compounds, because most of the bonds that are in those molecules are nonpolar bond, and water is a polar solvent. Okay, so that's why they don't mix. Organic molecules, such as glucose, that have polar groups are soluble in polar solvent, even though they have many carbons hydrogen bonds, but also they have oxygen hydrogen bonds. We can see here the molecule of glucose, uh, the black sphere is carbon, white sphere hydrogen. We can see that we have plenty of carbon hydrogen bonds, but also we have one, two, three, four, six atoms of oxygens, and we have at least one hydrogen in each of them. So we have six OH molecules um, in this or part in this molecule, and what type of bonds those OH could create with water. Hydrogen bonds. Remember that these hydrogens of oxygen specifically, they are polar. This hydrogen oxygen bonds are polar, so that this hydrogen could be attracted by lone pairs of oxygen in the water, or also this oxygen has two lone pairs that could attract um, a hydrogen from water, creating those hydrogen bonds that could help make glucose soluble in water. Also, we have the ascorbic acid known as vitamin A. We have here a group of carbons here and hydrogen atoms, but also we have oxygens that as well they can create those hydrogen bonds with water and make that vitamin A soluble in water. Molecules with long non-polar regions and polar regions act as surfactants, bringing polar material into aqueous solution used in detergents and soap. So basically what we are saying here is that some molecules that has two types of tails. This tail basically is an hydrophobic tail. This tail doesn't like water, but this head is known as a hydrophilic tail. This hydrophilic tail could be in contact with water. So a bunch of these molecules can create what is called the micelles. You're going to see in a few minutes a video that's going to explain a little bit more of this. And inside those micelles, you can trap any kind of non-polar molecule. And because all of this polar or hydrophilic heads are going to be like surrounding that, is going to make that non-polar molecule soluble in water. So let's see the following video to explain this a little bit. So we have also the another concept that is known as the acid-base properties. And many organic molecules contain acidic or basic functional groups. One of them is known as the carboxylic acids. This is COOH, carbon, double bond oxygen, oxygen, and hydrogen, are the most common acids in organic chemistry. The amines, basically, sorry, this is an example of carboxylic acid is known as acetic acid or ethanoic acid. Here we have the carbon oxygen, oxygen, hydrogen. Usually it's the carbon double bond oxygen. This is known as the carboxylic, and carbon bond by the making a bond with OH. So this is a functional group known as the carboxylic acid. Another one is the amines. These are basically organic compounds with nitrogens, where we can have like NH2, NHR, or NR2, where R is an organic group made of carbon and hydrogens, also known as an alkyl group. We're going to see that in a few more slides. And the amines are the most common bases in organic chemistry. And we have here ethylamine. We have this NH2 is the amine. So this is the basic part of this molecule. So this molecule is known as a base in organic chemistry. The hydrocarbons. Hydrocarbons consist of only carbon and hydrogen atoms. If you have a molecule just with carbon and hydrogen, that molecule is known as hydrocarbons. They are grouped based on the number of bonds between carbon atoms. There are four basic types of hydrocarbons. The alkanes, that all the alkanes are molecules that just have single bonds between carbon or carbon and carbon. We have the alkenes. The alkenes are molecules that have double bond between carbon and carbon. In a molecule, if you have at least one double bond between two carbons, that molecule is an alkene. A hydrocarbon is not like alkene specifically. The alkenes is basically a triple bond between carbon or carbon in the hydrocarbon. So if you have a triple bond between carbon and carbon, that is molecule is known as a alkene. And finally, the aromatic hydrocarbons. These are six member carbon ring. Okay, we have a ring here of 6 atoms of carbon, and also we have this. You can see the circle here means that we have double bonds between all this carbons. So it's known as an aromatic hydrocarbon. So we have the alkane, alkene, alkyne, and the aromatic groups. Properties of hydrocarbons. Since they are nonpolar, they are insoluble in water, but soluble in nonpolar solvent. Why are they nonpolar? They are nonpolar because all the bonds that they have are between carbon, carbon, hydrogen, and carbon, and those bonds are nonpolar. So that's why those molecules are nonpolar. That means that the melting points and boiling points are determined by dispersion forces. Low molar mass hydrocarbons are gases, moderate molar mass hydrocarbons are liquid, and high molar mass of hydrocarbons are solid. Here we have a table of the first 10 members of the straight chain alkane series. The CH4 is called methane. You see the boiling point is minus 161 degrees. Ethane, that is with 2 carbons, is minus 89. Propane, minus 44. Butane, minus 0.5. Pentane, 36 degrees. Hexane, 68. So as you can see, as you increase that chain of hydrocarbon, also the boiling point is increasing. So for 1 carbon is methane, for 2 carbon ethane, for a chain of 3 carbon is propane, 4 carbon is butane, 5 pentane, 6 hexane, 7 heptane, 8 octane, 9 nonane, and 10 decane. So you can these are the names of the first 10 alkanes, straight chain alkanes, that you are going to remember and use. Now, uses of some simple alkanes. Methane. Methane is a natural gas, is usually used as a heating fuel. Another one is propane. Propane is the one that has 3 carbons. And this one is usually used in bottled gas used to heating and cooking fuel. We have the hydrocarbon of 4, that is butane. This one is in the disposable lighters and fuel canisters for camping. Usually you can see this in any or whatever you go, if you want to go to camping or something, used for lanterns or also for for cooking, you can use this small type of tank. And alkanes from 5 to 12 carbon, the length, usually they are part of gasoline. So they are useful as a gasoline, or they use as gasoline. Now let's learn the method for writing formulas. There are a few common methods for writing these structures in organic chemistry. The first one is the structural formulas. This is where you show just how atoms are bonded to each other. So here we use bonds between the atoms. We have a carbon here, and there is a bond between these two carbon. There is a bond between this carbon and hydrogen, carbon, hydrogen, carbon, hydrogen. Remember that hydrogen can make just one bond. That's why you can see here that they are just attached once with carbon. While carbon can create four bonds, it doesn't matter if it can be with three hydrogens and one carbon, or with two carbons and two hydrogens, as we can see here. So this basically is the structural formulas where you can see the bonds that are in those molecules. The other one is the condensed structural formulas, that this one doesn't show the carbon hydrogens bonds. Okay, they condense them as to group in like CH3 or CH2. So this whole thing, if they don't show this bond, so it's a CH3. This has two hydrogens, so this is a CH2, two hydrogens, CH2, three hydrogens, CH3. So CH3, CH2, CH2, CH3. All you can also represent it like this. So these two are known as the condensed structural formulas, and this one is the structural formula where you can see the bonds between the carbons and the hydrogens. So let's talk about the structure of alkanes. Carbons in alkanes are sp3. The hybridization of those carbons are sp3, and it is known as the geometric is tetrahedral, and they have bond angles between those carbon hydrogens bonds of 109.5. So basically here the angle is 109.5. The tetrahedral geometric structure, okay, of sp3 atom. In the straight chain form, all carbons connect in a continuous chain. Carbon can make four bonds, as I mentioned before. So it is possible for a carbon atom to bond to 3 or 4 carbon atoms, making a branch alkane. Compounds with the same molecular formula but different connection of atoms are called structural isomers, as seen on the next slides that we're going to see in a few seconds. So here we have, for example, this one is propane. We have 1, 2, 3 carbons. Okay, and this one is a CH3, CH2, CH3. Okay, so the structural formula, condensed formula is CH3, CH2, CH3 for propane. So here we're going to have mentioned a few structural isomers. So first we have the butane. In the butane we have 4 carbons. We have 1, 2, 3, 4 carbons, and we can see that we have 3 hydrogens in the first carbon, 2 in the second, 2 in the third, and 3 in the fourth. So we have here CH3, CH2, CH2, CH3. So here we have the condensed structure formula for the butane. Now, there is another option for molecules that have 4 carbon, and it's this one. In this one, we have a change of 3 carbons, and instead of one CH2, one of the hydrogen has been substituted with a CH3. So here we have propane, because the longest chain now is of 3 carbon instead of 4. If the longest chain, straight chain, is 4, is butane. But here the longest chains that we can produce is 1, 2, 3 is propane, or 1, 2, 3 is propane. 1, 2, 3 is propane, is the same. So it's 1, 2, 3 propane, and we substitute one hydrogen of this carbon for a CH3 group. Usually this is known as methane, but because it's a substituent, it's called methyl. So you're going to add a YL instead of A and E. So this is in the position number 2, 1, 2. So it's a 2-methyl propane. Okay, so this and this are structural isomers. They have the same molecular formula, but the arrange of them is different. This is a change of 4 carbon. This is a change of 3 carbon and 1 substituent. Now let's see the hydrocarbon of 5 that is known as pentane. And pentane, we have 5 carbon, 1, 2, 3, 4. This is 5. This is straight chain. CH3, CH2, 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 CH3. Okay. Now, we also can create another structural isomer from this one. So instead of a 4, let's create a 5 chain carbon. Let's create a 4, and let's substitute one of this hydrogen of this carbon to a methyl group. So here we have 1, 2, 3, 4. This is butane, and the position 2 we have a methyl. So it's 2-methyl butane. That's the name of this compound. And these two molecules, the pentane and the 2-methyl butane, are known as structural isomers because they have the same molecular formula, but the arrangement, the connections is different between the atoms. And also we have a third structural isomer for this compound that is known as 2,2-dimethyl propane. In this one, the longest change is a 3 carbon. And now this carbon has 2 substituents. There are 2 methyl groups. So we have 1, 2, 3. This is propane. And we have 1, 2 methyl groups in the position 2. So that's why it is said 2, 2. This one is in 2. This one is in 2. We need to give for each substituent one number. So that is why 2, 2 dimethyl, because we have 2 methyl group, they are the same, dimethyl propane. So we have 1, 2, 3. The longest change that you can create here is of 3 carbons, and the substituents are in position number 2. 1, 2, 3. So we have 1 methyl group in position 2. Propane and 2,2 dimethyl propane. That's the name of this isomer. So all of these 3 compounds, they are structural isomers for pentane, for a hydrocarbon of 5 carbons. So let's talk about the systematic nomenclature for organic compounds. There are 3 parts to a compound name. Number 1 is the base. The base, this tells how many carbons are in the longest continuous chain. Okay, so that's basically the base. The suffix, this tells what type of compound it is. And the prefix, this tells what groups are attached to the chain. So we have here the base. The base tells how many carbons we have. The suffix is what family, if it has alkane, alkene, alkyne. So we're going to see in a few slides the suffix, and the prefix here tells us what groups are attached to the change, the substituent of the change. So let's see how to name a compound. Number 1, find the longest continuous chain of carbon atoms and use this as the base name. So we have here, for an example, a change of 1, 2, 3, 4, 5, 6. We also have a change here for 1, 2, 3, but this is not the longest change, so that's why we can use this one. You can say maybe that we have 1, 2, 3, 4, 5, 6. So also, if you start here, it's basically the same number of chain of carbon for the chain as if we start here. So basically, if you start from here or here, is the same length for this chain. The second one is number the chain from the end nearest to the first substituent encountered. So another thing that usually I do is like once I identify the longest change, I put this change in a bubble. Okay, so that will let me know if we have substituent, because right here we have something that is outside the bubble. So this is a substituent. So that helps me to see visually which ones are the substituents in this molecule. So we can see here that we have a substituent here. So we can start by here or also by here. If we start here, this will be 1, 2, 3, 4, 5, and our substituent will be in the number 5. But if we start 1, 2, our substituent will start number 2. So we need to give our substituent the lowest numbers possible. Okay, so that's why we start here instead from here. And name each substituent. Side chains that are based on alkanes are called alkyl groups. So that's why this is a methyl group. So that means that for methane is methyl. If we have an ethane is ethyl. These are substituents, okay? If we have a propane is a propyl. If we have butane is a butyl. If we have an isopropane is isopropyl, or terbutane is terbutyl. So here we have this one is come from methane, so it's a methyl. So it's 1, 2, 2 methyl, and we have a change of 6 hexane. So that's basically the name of this compound, 2 methyl hexane. Now, we can have also complicated structures like this one, but you need to follow the same rule. Look first for the longest chain. That's the first rule. So we have here 7. We can start 1, 2, 3, 4, 5, 6, 7 also here, but we need to look for the longest chain that has the higher number of substituents. And if we use this 7 here, 1, 2, 3, 4, 5, 6, 7, we're gonna just have 1, 2, 3 substituent. That's why we use this as the longest chain, because using this one we have 1, 2, 3, 4 substituents. So beginning the name with the numbers on the carbon atoms to which each substituent is bound. Then when 2 or more substituents are present, list them alphabetically. Sorry. So here we have 1, 2, 3, 4, 5, 6, 7 is an heptane. So we have here basically the suffix heptane. We have basically this the base is hept because we have 7, okay, carbon. So it's heptane. Basically tell us what type of organic molecules we have. This is an alkane, and the substituents we have 1, 2, 3, 4. Now we can start from here or also from here, but remember that we need to give the lowest number to the first substituent. So if we start from here, this point was here, 1, 2, 3. This will be a 3. If we start from this side, 1, 2, this will be a 2. So we start from this side. That's why we start here instead of here. So we have 1, 2, 3. So in the number 2 and number 4 and number 5, we have the same group. It's called methyl group. We have 3. So that's why it's trimethyl group. Okay, and we need to also show the number where they are. 2, 4, 5. So it's 2, 4, 5. If we have 2 methyl groups here, remember that we need to use 2, 2, 5 trimethyl group. Okay, even though they are the same, we need to give one number for each, even though they are in the same carbon. Okay, and the ethyl group is 3 ethyl. So we have 1, 2 ethyl that's come from ethane, but it's a substituent. So that's why we use the "il" at the end of the name. So 3 ethyl, 2, 4, 5 trimethyl heptane. Because E is go first at the M, we use the ethyl first and then the trimethyl in the second position. Let's talk now about cycloalkanes. The cycloalkanes are alkanes that form rings or cycle. This could be possible with at least 3 carbon atoms, but sp3 hybridization requires 109.5 angles. So these are not very stable molecules. You can create something like this, okay, a ring with 3 carbons, but it's not very stable because we have a lot of tension here because this is lower than 109.5 angle, okay? Also, you can represent the cyclopropane as this or as this, where each vertex is a CH2 group, okay? So each vertex here we have a CH2 group, so we have 3 CH2 group here. That's why this one is cyclopropane. The 4 carbon ring is also not very stable. 5 carbon and more have room for proper bond angle. So here we have cyclopentane because we have 1, 2, 3, 4, 5 carbon. This is known as cyclopentane. Remember that each of this vertex is known as a CH2. And we have also the cyclohexane. The cyclohexane is a a ring of 6 carbons, and the same thing, each word is here represent a CH2. And to name it, we just need to add cyclo as a prefix to the alkane name. If it's from 5, from 4, from 7, cycloheptane, and so on and so on. So let's talk about reaction of alkanes. Alkanes are relatively unreactive due to the lack of polarity and presence of only carbon-carbon bonds and carbon-hydrogen sigma bonds, which are very stable. So that's why they are not very reactive. They do not react with acid, bases, or oxidizing agents. They are really, really stable. However, the most important reaction observed is the combustion. Here we have um, this one is 2 carbon, so this is ethane. Okay, ethane here, 2 ethane molecules of ethane plus 7 molecules of oxygen produce 4 of CO2 plus 6 of water. So you can see here that for each carbon that you have in the molecule, you're going to have produce 1 CO2. So we have here a total of 4 carbons. So we produce 4 carbon dioxide. And really interesting is that this type of reaction is an exothermic reaction. That means that release a significant amount of energy. So no wonder most of the alkanes are used as fuel. Propane, butane, octane, because these are really, really exothermic reaction, so release a lot of energy, so can be used as fuel. Now there is another characteristic for hydrocarbons. They could be saturated or unsaturated. Hydrocarbons with single bonds only are called saturated hydrocarbons. These are the alkanes. All the alkanes are saturated. You're going to find just single bonds between those carbon-carbon atoms. Alkenes, alkynes, and aromatic hydrocarbons have fewer hydrogen atoms than alkanes, with the same number of carbon atoms. They are called unsaturated hydrocarbons. So if you see at least one double bond or one triple bond in a molecule, that molecule is, or that hydrocarbon is an unsaturated hydrocarbon. Unsaturated hydrocarbons are more reactive than saturated hydrocarbons. So let's talk about alkenes. Alkenes is the first unsaturated hydrocarbon that we're going to talk. It contains at least one double bond in between carbon or carbon. Because of that, there is no free rotation between this carbon. Here, there are no rotation. In the other sigma, when you just have sigma bonds between a carbon, hydrogen, carbon atom, you have rotation continuously there. But here, when you have a double bond, you don't have rotation. To naming alkenes, this is basically the same as alkanes. The longest chains must include both carbon atoms that share the double bond. This is really important. The double bond must be, both carbons needs to be part of the longest chain. And the N name, you're going to use an E and E instead of A and E. And the lowest number possible given to the double bond carbon atoms. Okay, so you're going to look for the longest chains that contain both atoms of carbon that create the double bond. You're going to use the E and E and for the name as a prefix and or suffix, excuse me. And also you need to give the lowest number possible to the carbon of the double bond. And also if there are isomers, and we're going to see that this in a few minutes, we need to indicate the isomer for that alkene. Here we have a representation. In the middle, we have an alkane. Okay, we have just single bonds. And if we can remove those, basically here, we can create 2 double bonds. One where 2 hydrogens are in the same side. Okay, when we have 2 hydrogen, this is the double bond here. This 2 hydrogen is in the far side of the screen. They are in the same side, so this isomer is called as the cis isomer. And if the hydrogens are opposing each other, okay, in the different atoms, not in the same, in different atom, this is called a trans isomer. Okay, so we need to have at least one hydrogen in each of the carbon, okay, and we need to see what is the orientation between them. If they are in the same side, it's called the cis isomer. If they are in the opposite sides, this is the trans isomer. And they are isomer because they have the same number of atoms, they have the same molecular formula, but the orientation of those hydrogens are in different. Okay, here we have in the same side is a cis, and here we have in opposite sides that is known as the trans isomer. So these are known as geometric isomers. Since there is no free rotation around the double bond, the direction of the longest chain can differ for four or more carbon atoms. Compounds that have all atoms connected to the same atoms but differs in three-dimensional arrangement are geometric isomer. And the alkenes have two different geometric isomer. The cis, that is where they are in the same side of the double bond, or the trans when they are in the opposite side of the double bond. These are known as the cis trans isomer. So here we have one example. This one doesn't have any cis or trans isomer because we have the same groups in each carbon. So that means that we don't have a difference here, neither here. So we don't have here an cis trans isomer. This one is called 1,2,3 propane, and this one is a methyl group. It could be this one or this one. It's in position 2,2-methyl propane. Here we don't use the number 2 because there is no other option for a methyl group to be in this compound. So it's methyl propane or 2-methyl propane is okay to use. Now here we have 1, 2, 3, 4. The longest chains that contain that double bond is from 4 carbon. So this is butene. And here we have, this also doesn't have any cis trans isomer because even though we have two different groups in this carbon, we have the same group in this carbon. So that's why we don't have a cis trans isomer, neither here and neither here. Okay, if we have in the same carbon two groups that are the same, you can't have a cis trans isomer. Now let's see this one. We have here 1, 2, 3, 4. This is butane, but now this double bond is inside the chain. Okay, so we need to give the number for the first carbon of this double bond. So it is 1, 2. So that's why it is 2 butane as different from this one. This is an external double bond. This is an internal double bond. The external bond basically are in the corner of the chain, while the double bonds are inside the chain. So, and because it's inside, you need to specify the position of that double bond. So that's why 1, 2, this is cis 2 butane. Why is cis? Because we need to check the carbon of the double bond. We have different groups here. We have different groups here. Okay, let's see the hydrogens. They're the same side. So this is a cis 2 butane. Okay, so we have 1, 2 cis butane. And here we have basically 1, 2, 3, 4. And we have the hydrogens that are on opposite sides. So this is a trans 2 butane. Okay, so we have 1, 2, 3, 4. And we have the double bond in the position number 2, and the trans for this type of isomer. So this and this are cis trans isomer. This doesn't have any type of cis trans isomers. So let's talk about the alkynes. The alkynes contains at least one triple bond between two carbons, and also is unsaturated hydrocarbon because we have at least a triple bond. When we have unsaturated is because we have less number of hydrogen than in a saturated compound. To name in this alkynes, longest continuous chain containing both carbon atoms in the triple bond, the same concept as the with alkenes, and name ends in YE, okay, instead of ane, and ene is eine, and give the carbon atoms in triple bond the lowest number. Okay, the same number, the same rule for the alkene is to alkyne. Here we going to assign to the one of this carbon the lowest number possible. Okay, and they need to be, those two carbons need to be part of the longest continuous chain. So here we have an example. Here we can have two chains. Actually, we can have just one really long chain. Is 1, 2, 3, 4, 5, 6, 7, and this one is 1, 2, 3, 4, 5, 6. So even though we have a chain that has a larger number with 7 carbon, we need to choose this one because the rule says that the triple bond needs to be part of the longest chain, continuous chain. So our chain is 1, 2, 3, 4, 5, 6. So this one is hex because this comes from hexane, but because it's a triple bond is hexine. Okay, and we have a substituent in 1, 2, 3. Position number 3 is a propyl group, so it's 3-propyl hexine. This is the name of this compound. Now the alkenes and alkynes, the reaction that they have experienced are addition reactions. In the addition reactions, we add atoms to the double or triple bond, making it saturated or more saturated. The p bonds are broken and electrons from the sigma bonds to added atoms. Okay, so p bonds atoms are broken and electrons from sigma bonds to added atoms. So most of the addition reaction are known as hydrogenation, where we add hydrogens, hydrogen halides or water, and halogenation. The first one, that is the this is halogenation. We're adding 2 bromines, so we're going to add 1 bromine to each of the carbon that are part of that double bond. Okay, so when we add Br2, we're going to add a bromine here and a bromine here, and this is our addition product for um, ethane, ethene, ethene. Here we have the butene with hydrogen, this hydrogenation. We're going to add a hydrogen to each of this carbon, and when we do that, we're going to create a CH2 here and a CH2 here. So as you can see, the product of this one and this one are saturated compounds. We started with unsaturated compounds and we created saturated compound by adding the bromination and here the hydrogenation. Also, we can add water with sulfuric acid, and the water is created with hydrogen and OH, so we can put 1 hydrogen and 1 carbon and the OH in the other one, and this will create this molecule that is an alcohol. Okay, and this is a saturated one. Okay, so all of the addition reactions for alkenes or alkynes make the compounds more saturated. And here we have the butene. Okay, we have a triple bond, and we're doing the halogenation. So we are adding chlorine. We are adding 1 chlorine to each of the carbon that are part of that triple bond, and we can create this one. So here we decrease the unsaturation, okay, but it's still unsaturated. But from a triple bond, we create a double bond, and in this case, we create a trans 2,3-dichlorobutane, okay, 2-butane, because we have the 1, 2, 3, 4 chain is butene is in the position number 2, 1, 2, and we have 2 chloride that is in position 2 and 3, so it's 2, 3 dichloride, and because they are in opposite side, okay, is a trans 2, 3 dichlorobutane. So let's talk about the aromatic hydrocarbons. Aromatic hydrocarbons have 6-membered rings containing localized and delocalized electrons. The p of the pi ring is much more stable than the pi bond. So aromatic hydrocarbons are much less reactive than alkenes and alkynes. They are really much less reactive than those types of compounds, organic compounds. They undergo substitution reactions rather than addition reactions. In the ones of alkenes or alkynes, we add, for example, in hydrogenation, we add two hydrogens. In halogenation, we add two halogens with two bromines or two chlorine. Okay. Now here in the aromatic hydrocarbons, they undergo substitution reaction. So groups replace hydrogens on the ring. We have nitrations, halogenations, and alkylation. In nitration, we use nitric acid in H2SO4, and here we just add NO2, okay, from the benzene ring, and we have this substitution. So we are substituting one hydrogen. Remember, here we have in each vertex, in here, this vertex instead of CH2 are CH. So we are removing one hydrogen and putting there an NO2 from the nitric acid. The other one is halogenation. So a bromine is substituting one hydrogen from here. So we can put the bromine in that carbon. And it doesn't matter, the six hydrogens are the same. So it could be this one or this one or this one, it doesn't matter. You could put the bromine here or the bromine here. So it's basically the same, bromobenzene. Here we have a nitrobenzene, bromobenzene, and the alkylation, it's when we add alkyl group, okay, that's this one. So we substitute once again one hydrogen from any of these six, and we put there the ethyl group. So we have ethyl benzene. These are basically the three reactions for the aromatic hydrocarbons: nitration, halogenation, and alkylation. And the nomenclature for the aromatics compounds. Many aromatic hydrocarbons are known by their common names. Others are named as derivatives of the benzene. And sometimes we're going to have more than one substituent in the uh, benzene ring. So we're going to use, if they are in position 1 and 2, we can call them ortho. If they are position 1 and 3, we can call them meta. And if they are in 1 and 4, we can call them para. So here we have a 1,2 dinitrobenzene, or also ortho dinitrobenzene, because they are in position 1 and 2. So this one could be called ortho dinitrobenzene or 1,2 dinitrobenzene. If they're in 1 and 3, as this one is 1,3 dinitrobenzene or meta dinitrobenzene. So those are the position relative to those substituent in 1 and 2, 1 and 3, and 1 and 4. This will be the para-nitrobenzene, okay, or 1,4 dinitrobenzene. So we have the benzene ring, and sometimes there are fusion of benzene rings. We have here the naphthalene, for example, also the anthracene. This is the toluene, a methylbenzene. Okay, we have the benzene ring here and the CH3, and we have also the paran here. These are different compounds of derivatives from the benzene ring. And with this, we'll finish our model number 24, the first part of model 24.